Hey everyone, and welcome to this explainer. Today, we're going to completely reframe how we look at math. We're not just going to talk about abstract numbers or dry textbook theories. Instead, we're looking at trigonometry as a brilliant detective's toolkit. It's literally a method for finding the missing pieces of the world around us. Whether it's a leaning ladder, a towering skyscraper, or a rocket blazing through the sky, these tools allow us to take a few tiny clues and deduce the entire picture.
So, here's our roadmap for today. First, the trigonometry toolkit. Second, decoding complex geometric shapes. Third, real-world triangle puzzles. And finally, testing your trig knowledge.
Let's dive right into Section 1, the trigonometry toolkit. Consider this your basic training.
Okay, so the absolutely crucial point here is understanding our primary mission, which is solving a right-angled triangle. Basically, this just means finding the values of all the remaining angles and sides. And the cool part? We don't need all the information to do this. We just need a couple of specific clues, like one side and one acute angle.
Let's see how elegantly this works in practice. So looking at our first case, we have a right-angled triangle at B, and we've got only two clues. Side BC is 20 centimeters, and angle A is 30 degrees. Now, from just those tiny fragments, our goal is to deduce the exact length of the unknown side, AB.
To do this, we follow a super simple three-step deductive process. Step 1. Identify the knowns. For us, that's our base, BC, and our angle. Step 2. Choose the ratio that links our clues to our target. In this case, it's cotangent. And step 3. Calculate. The cotangent of 30 degrees is the square root of 3. So, a quick multiplication gives us our exact answer, 34.64 centimeters. Boom! Case closed.
Moving right along to Section 2, decoding complex geometric shapes, or as I like to call it, triangles in disguise.
Now that brings us to a really vital question for any visual detective. How do our trigonometric tools work if the puzzle we're looking at isn't a triangle at all? What if it's, say, a rhombus or a trapezium?
Well, this illustrates our primary tactic, unmasking shapes. Take this rhombus, for example. We're told its sides are 10 centimeters and angle A is 60 degrees, and we need to find the lengths of its diagonals, AC and BD. Now, at first glance, there are literally 0 right triangles here. But remember, the diagonals of a rhombus always bisect each other at exactly 90 degrees. By just drawing those diagonals, we've instantly created 4 distinct right-angled triangles hiding inside the rhombus. Now we can easily use sine and cosine to find the missing diagonal lengths. That complex shape? It was just right triangles in disguise the whole time.
And we see this exact same trick used with a trapezium. It's got this awkward 120-degree angle, which seems tricky at first, but look at the strategy here. Simply draw a perpendicular line straight down from corner C. Aha! Instantly, that intimidating trapezium is sliced into a friendly rectangle and a perfectly solvable right-angle triangle. By finding the sides of that new triangle using the sine and cosine of 60 degrees, the whole puzzle just completely unravels.
So this brings us to a really fascinating logic puzzle. Statement 1 asserts that in a rhombus with 20 centimeter sides and a 120-degree angle, the short diagonal is exactly 20 centimeters. Statement 2 tells us we can prove this because in the inner triangle, the cosine of 60 degrees gives us the key ratio. Well, through the tools we literally just discussed, dissecting the rhombus into right triangles, we can definitively prove that both of these statements are absolutely true, and the reasoning is mathematically rock solid.
All right, on to Section 3, real-world triangle puzzles. It's time to put all this into practice. Imagine you're tracking a high-speed rocket. It's an incredible scenario. A rocket is fired vertically upward for 40 kilometers. Then, suddenly, it alters its course. It travels another 40 kilometers, but this time tilted at exactly a 60-degree angle to the vertical. We need to find out exactly how high the rocket is right now and how far horizontally it is drifted from the launch pad. So how exactly do we track it? We project a right triangle right up onto the sky. For step 1, we draw a perpendicular line from the rocket's final position back to the vertical axis. That sets up our whole scene. Moving to step 2, because the angle with the vertical was 60 degrees, the angle inside our newly drawn right triangle is 30 degrees. We can just use the sine of 30 degrees to solve for that extra vertical height. And finally, step 3, we use the cosine of 30 degrees to solve for the horizontal drift.
By executing step 2, we find that the second leg of the journey added exactly 20 kilometers of vertical height. We simply add that to the initial 40 kilometers of straight-up flight, and there's our answer. The rocket is precisely 60 kilometers high in the sky.
And what about its horizontal drift? Well, by using the cosine of 30 degrees, we can instantly deduce that the horizontal distance is precisely 34.64 kilometers away from the launch pad. Think about that for a second. We just solved a highly complex aerospace tracking problem using absolutely nothing but a pencil and some basic trig ratios.
And honestly, these kinds of everyday mysteries are everywhere. Using these exact same tools, we can measure the length of a 50-meter tower shadow just by knowing the sun's altitude. Or we can calculate the exact length of a leaning ladder. Or even determine the absolute greatest height a kite reaches when it's attached to a 100-meter string. The applications are just incredibly universal.
Which brings us to Section 4, Testing Your Trig Knowledge. This is your final mission.
Yep, for your final mission, we're going to look at a case study scenario bringing the math all the way back down to an everyday playground. The setup is simple. A school authority constructed a slide for its children below the age of 12 years.
Here is your crime scene photo, along with all the visual clues you're going to need. The slide has a vertical height of exactly 4 meters above the ground. The slope of the slide is inclined at an angle of exactly 30 degrees to the ground. So you have a right angle, you have one side, and you have one acute angle.
So I leave you with this cliffhanger to solve on your own. Using your brand new trigonometry toolkit and knowing that the sine of 30 degrees relates the opposite side to the hypotenuse, what is the exact total length of that slide? Take a look at the clues, run the ratio, and see if you can crack the final puzzle. Thanks so much for joining me on this explainer, and definitely keep using those tools to decode the world around you.